Hi everyone, this video is about recurrence relations. So in this video we'll talk about what recurrence relations are and give some examples, including the Fibonacci sequence, and then we'll talk a little bit about how to model with recurrence relations. So in most of your prior experience with functions, you've been given a rule in the definition of the function that allows you to compute an output immediately for any given input. For example, let's suppose we have a function from the natural numbers to, say, the integers, where f of n is going to be n squared. So this rule, it tells us immediately how to compute an output for any given input. Like, for instance, if the input is 7, then I know immediately, because of this formula, f of n equals n squared, that the output is 49. Now, in this chapter, we're going to be discussing a different type of way of defining functions. So the functions we're going to be talking about in this chapter, their domain is always going to be the natural numbers. And instead of giving a rule that allows us to immediately compute the output for any given input, our function definitions rather are going to be self-referencing. So sort of a self-referencing function is called a recurrence relation. Okay, now what do we mean by that? So here, in the bottom of the slide, we have a recursive definition for a function, p of n. So p of n, that's supposed to tell us what the output is for a given input n. And we see that if n equals 1, we know immediately what the output is. It's equal to 1. However, if n is anything bigger than 1, then we're given this formula down here that relies upon us knowing the value of p of n minus 1. So evidently here, in order to know what p of n is, we must first know what p of n minus 1 is, and so on and so forth. So let's take a moment here and see if we can evaluate p of n for some inputs. So, for instance, we know that p of 1 is equal to 1 because that's the top branch of this function. P of 2, well, now we're in the bottom branch of the function. 2 is bigger than 1, so apparently p of 2 is going to be 2 plus p of 1. But we already know what p of 1 is. It's just 1. So p of 2 should be equal to 3. And then we could do p of 3, which would be 3 plus p of 3 minus 1. So 3 minus 1 is 2, so we are taking 3 plus p of 2. But we already know what p of 2 is, right? P of 2 is equal to 3, so this is 3 plus 3, which is equal to 6. So on this slide and the next, we're going to compute some more specific values of the recurrence relation here that we defined on the previous slide. So this time, we're going to compute p of 5. Okay, now the method here is called bottom up, which is very much like the method we were employing on the previous slide. So here, this recurrence relation tells us values of p of n, provided we know the value of p of n minus 1. So here, as on the previous slide, we know p of 1 is equal to 1. And again, just like we did previously, p of 2 is going to be equal to 3. P of 3 is equal to 6. Now, repeating the process, we get p of 4 is 4 plus p of 3, right? Remember, That's how we find P of 4, is to take 4 plus P of 3. But P of 3, remember, was equal to 6. And when we take 4 plus 6, we get 10. And then finally, P of 5 will just be 5 plus the previous value of P, which was 10, which is 15. Now we find P of 5 using what's called the top-down method. So we start with P of 5, which is the thing that we want to get, and we see that that's 5 plus P of 4. And so now the problem has shifted to figuring out what P of 4 is. Well, according to our recursive definition, P of 4 is 4 plus P of 3. And now the problem has shifted to figuring out what P of 3 is. But P of 3 is 3 plus P of 2. And P of 2 is 2 plus P of 1. And finally, we know what P of 1 is. It's just 1, right? So we can replace the P of 1 by 1. And then we see that P of 5 is obtained by adding all of the natural numbers 5 and less. It's 5 plus 4 plus 3 plus 2 plus 1, which gives us 15. And notice that that's the same value that we got on the previous slide. One of the earliest and most famous examples of a recurrence relation comes to us from the 13th century, and it's due to the Italian mathematician Leonardo of Pisa, otherwise known as Fibonacci. So Fibonacci asked a certain question about rabbit reproduction, which is given in this paragraph. And apparently when one parses that paragraph carefully, it can be translated into a recurrence relation as follows. So when n equals 1 or 2, the value of f of n is equal to 1. And for any n bigger than 2, what you do to get the output is add the prior two values of f. So this sequence that's formed is called the Fibonacci sequence. Okay, so here we have the first several values in the Fibonacci sequence. So the first number is f of 1. The next number is f of 2, and so on and so forth. Now remember that to get f of n, it's just 1 if n equals 1 or 2, and it's f of n minus 1 plus f of n minus 2. When n is bigger than 2. Okay, so here, for instance, we see that f of 3 needs to be 2 because how do we get this 2? Well, we add together the prior two numbers. Okay, so now that tells us what f of 3 is. What about here, this number after 34? What should that number in the sequence be? Well, according to this rule given to us by Fibonacci, we are to add the prior two numbers. So I take 21 plus 34, and that gives us 55. And that is the next number in the list. For the next few slides, we'll be talking about modeling using recurrence relations. So first we have this example involving Ursula, the usurer, who is lending money at an outrageous rate of interest. So she demands to be paid 10% interest per week on a loan, compounded weekly. So let's suppose you borrow $500 from Ursula. If you wait 4 weeks to pay her back, how much will you owe? So we can phrase this in terms of a recurrence relation. So let's let m of n denote how much money we owe Ursula after n weeks. So if Ursula hands us the $500 and we hand it immediately back to her, then we're all square, right? However, if we wait some number of weeks beyond 0, then the amount we owe her in the nth week, because the interest is compounded weekly, is 1.10. Remember, it's 10% interest. So it's 1.10 times the amount we owed her the prior week. Okay, so that means that after 4 weeks, the amount we owe her is 1.10 times the amount we owed her after 3 weeks. And the amount we owe her after 3 weeks is 1.10 times the amount we owe her after 2 weeks. And so on and so forth. So this is this top-down method that we discussed on a prior slide of evaluating a recurrence relation. So at the end, we finally get down to a product of a bunch of 1.10s and m of 0. But we know what m of 0 is. It's 500. And so now finally we can calculate that the result, that is what we owe her after 4 weeks, is about $732. So now we're going to form a recurrence relation for the hexagonal numbers. So we're going to let h of n be the number of circles you need to form a hexagon with n circles on each edge. So what we have pictured here is the number of circles to form a hexagon with 3 circles on each edge. So to find h of 3, what we're doing is, well, first we notice that there are 3 circles on each edge, and now we're just going to count up the circles, right? So we get 3 plus 4 is 7, and 5 is 12, and then another 7 would be 19. So apparently h of 3 is 19, and what we'd like to know is a recursive formula for finding h of n. Okay, so the solution to this problem of finding hexagonal numbers is given here in the wording on this slide. And I would like you to read the solution and then focus your attention on the formula for h of n, giving the nth hexagonal number. Now, you might remember that on the previous slide, we determined that if you look at the hexagon with 3 circles on a side, then the total number of circles is h of 3, which was 19. So let's see if that lines up with the formula that we're given here at the bottom of the screen. So we know that h of 1, according to our formula, is equal to 1. And now h of 2, that is h of 2 minus 1, which is 1, plus 6 times 2 minus 6. Okay, so we're using now the bottom branch of this recurrence relation. H of 1 is equal to 1, so I get 1 plus 12 minus 6. So that would be 7. And then finally, we're ready to compute h of 3, which is h of 2 plus 6 times 3 minus 6. Remember, h of 2 was 7, so that's 7 plus 6 times 3 minus 6. And that indeed does give us 19, which is what we expected it to give us. So you might recall that if we start with a set X, we can form its power set. Remember, the power set is the set of all subsets of X. Now, in this problem, if X is a finite set that has n elements, then what we're going to do is find a recurrence relation for the number of sets in the power set of X. So according to this formula, right, if n has 0 elements, that is, if X just consists of the empty set, then the number of subsets of X is 1, namely just the empty set. And then if n is bigger than 0, we take the number of subsets in a set of size n minus 1, that's this, and multiply by 2 to get the number of subsets in a set of size n. So let's try to see why this might be true. So let's start by letting x sub n be maybe our favorite set of size n. Let's say it's the numbers 1, 2 through n. And we're going to also let x sub n minus 1, of course, be all the numbers up through n minus 1. And remember, that is a subset. It's a fairly large subset of x sub n. Now, what is the number of subsets of this set x sub n? Right? Okay, so Cn, remember, is the size of the power set. So that's the number of subsets of this set x sub n. And I could get a good number of those subsets by just looking at the subsets of x sub n minus 1. So let's start there. And then what I want to do is add on the number of the remaining subsets. So we have to ask ourselves, well, what subsets of x sub n are not accounted for in the subsets of x sub n minus 1? And those sets that are not accounted for are going to be precisely the ones that involve this last element, n. So what I could do is I could take any set or any subset of x sub n minus 1 and append an n to it to get one of these missing subsets of x sub n. And so what that means is that I take, any one of these subsets of x sub n minus 1 and append an n. And so the number of things that I get in that way, again, is just the number of subsets of x sub n minus 1. So I add those things together and I get 2 of these sizes of the power set of xn minus 1. But remember, the size of the power set, that's what we're calling C. So this would be 2 times Cn minus 1. And that's why the formula holds. So one, other thing we could do here is let's compute the values of C for a few numbers. So we know that C of 1 equals 1. C of 2 is going to be double whatever we had before. So that's going to be 2. So C of 3 is going to be 2 times C of 2, which is 4. C of 4 is going to be 2 times C of 3, which is 8. And you can see that what we're getting here is just powers of 2. And so C of n, if we want what we call a closed form formula for this function, is just 2 to the n. And you may recall when we were talking about sets a month or so ago that I asserted that the size of the power set of a set where that set has n elements is 2 to the n, and this is the reason why. So in this slide, we have an example where we want to count the number of nodes or vertices on a complete binary tree of depth n. So I'm not going to spend time on this example. What I'd like you to do is read through it and take a look. So here on this final slide, we're going to be talking about a recurrence relation for the number of edges in a complete graph. So first we need to remember what a complete graph is. So the complete graph K sub n on n vertices is an undirected graph that has exactly one edge between every pair of vertices. So our goal is to find a recurrence relation for the number of edges in Kn. So if n is equal to 1, that is, we have just a single vertex, right? Just a single vertex there. Then there are no edges. So En, the number of edges in the complete graph with one vertex, is 0. We have 0 edges. Now, what about if we have more than one vertex? Well, let's suppose, for instance, we start with a complete graph on n minus 1 vertices. So to picture that situation, I want you to imagine this K4 here, where we have these 4 vertices. And the complete graph is given by just all of these edges that join these 4 vertices. So between any 2 vertices, we draw an edge. Now what we want to do is imagine adding another vertex to take us from 4 vertices up to, say, 5. So we're now going to add this vertex right here. Now, how many edges do we need to include in order to get the complete graph on 5 vertices? Well, we already have all of the possible edges joining our original 4 vertices, and all we need to do is link up our additional vertex with the previous vertices that we had. So how many previous vertices did we have? Well, we had n minus 1 of them. And so that means I need to include n minus 1 edges to our new vertex. And therefore, the number of edges for the complete graph on K on n vertices is the number of edges for the complete graph on n minus 1 vertices plus n minus 1.